Hello, and welcome to an episode of ES Repair. I am your host, Mr. Fix-It. In this video, I'm going to be talking about power inverters and batteries. Now, I've been getting a lot of requests about running power inverters on batteries for an extended period of time, say 8 to 10 hours or, all night. Well, this will also help those who are running their stuff completely off of batteries, whether it's an inverter, light bulbs, radios, whatever the case may be. You can use the same stuff that I'm fixing to show you to calculate what you need to have as battery capacity to run your 12-volt devices. Well, I have been getting a lot of these requests about running inverters, so I will include the inverter on here. But if you're not concerned about the inverter part, but more of the battery part, you can still watch through the rest of the video. First thing is to understand power inverters. Now, if you're going to run stuff off of batteries, you need to understand how the battery is going to work. So, here are some things that you're going to need to consider. Now, if you are going to use an inverter, you need to determine what size of inverter you're going to be using. Now, the bigger the inverter, the more strain that it's going to be on the battery, which I will discuss later. You'll need to know the amperage that the inverter requires to provide the needed output power. The primary power source for the inverter, especially if you're going to use dual power sources, such as used in vehicles, to where you have an alternator and batteries, or if you're going to use wind electric generators or solar power, you need to decide how long the total hours the inverter will operate on batteries before recharge, or in this case, any devices that you're wanting to run on batteries for a long period of time. The battery type you'll be using. There are different types, disadvantages and advantages for each kind. You need to consider the time that it will be required to recharge the batteries before they can be used again. And then finally, we'll be discussing getting the most of the battery's life out of it, because you do know that over time they do become weaker. But I will discuss and show you ways to help improve and extend the battery's life. To start, power inverters are classified by the wattage they provide, and they do range from 75 watts to as high as 3,000 watts or more. To determine the size of power inverter needed, you'll need to add all the watts of the devices connecting to the inverter together. Now, if you're not going to use the inverter, but you're going to use 12-volt devices, you'll need to consider all the amperage that all the devices will use together. For inverters, you'll need to know all the watts. You'll also need to calculate the power requirement for the inverter. Now, most inverters are 87% efficient and does vary between the inverters. Be sure to read and provide a documentation that came with the inverter for efficiency. Keep in mind that the higher the efficiency means less power consumption. Now, not all devices will list their wattage. For an example, in this frame here, you see two pictures on the right hand side. These are taken from power supplies. One on the bottom is from my laptop, and the one on the top is from my external hard drive. Now, as you can see, they do not list the wattage. Well, in that case, all you have to do is just multiply the input voltage, as you see on the display, and multiply it by the amperage. In this case, at the top, you'll see the input can range between 100 to 240 volts, but the maximum current is only 700 milliamps. If you see a voltage amperage or the VA, don't worry about it. We're not going to be working with that. What you need to know is the amperage or milliamps. 1000 milliamps is 1 amp. And this one here used like 700 milliamps. The bottom one, which is from the laptop, it uses 1.5 amps. This is what you have to keep an eye on. Don't do the figure out the output one. You need to know the input of the power supply that you're using, or the device that you'll be using. So just multiply its input voltage, which is in most cases, depending on where you're at, it's usually 120. In other countries, it's 240. And just multiply the input voltage times its input current, and that will give your wattage. Now, once you know your total watts, get the inverter that will provide the wattage or more. Now, once you have your inverter, we need to calculate how much current the inverter will need to provide that output watts. Here is the formula to figure this up. Now, if you watch my all about power inverters, or powers inverters, I got several videos on those, including applications they can be used for. You'll notice that I've used this formula before, and it's very simple to use. The I, N, represents the amperage that the inverter will need. The equation is the watts output, which is the output of the inverter, divided by the result from multiplying the voltage in, which is the 12 volts, of course, you're running it off a battery, times the efficiency, which is the efficiency that the inverter uses to convert DC to AC, and most of the time it's 87%, but you may see them range between 84 and 88. But the higher, the better. Now, we're going to use my inverter, which was a 1500 watt picture that you see in the beginning of the video. Now, that inverter is 1500 watts. Now, it's going to be running, let's say, 12 volts. It's going to run off a battery. Now, I've showed you this in the previous videos. So, let's go ahead and substitute the 1500 watts. Then we substitute the voltage in for 12 volts. And then finally we substitute efficiency with 87%. So this is what your equation will look like. Now first, if you remember order of operations, we need to do the problem inside the parentheses first, which in this case will be 12 times 87%. This will give you 10.44. Okay, now we just substitute that. Now finally, all we have to do is divide 1500 watts by 10.44. This will give you 143.6 amps. Which means that this inverter will require 143.6 amps or 144 amps. This is to provide that the input voltage is at 12 volts DC. And this is to provide 1500 watts of power on the output. So for your inverter, this is how you would calculate how much current the inverter will need from the batteries or the power source, whichever you're going to be using. Now, the power source is an important factor. It must be able to supply a steady voltage and current to the inverter. The inverter can be powered from anything that provides 15 or 12 to 15 volts DC and provide the amperes the inverter draws to provide power. Now, you can use dual power, as I mentioned before, like a vehicle. Vehicles have dual power. They can either run off a battery or run off the alternator. Now, if you're going to do this in a vehicle with an inverter, you need to make sure that the alternator is big enough or has large enough amperes to be able to run the electrical system and be able to charge your batteries along with your inverter. Now, as I mentioned here, now when your engine's running, your alternator is working. It's running the entire system. But when you shut the engine off, then everything that turns on is running off the battery. Now you have other sources, such as wind electric generators, which I've had a lot of requests over, solar electric generators. All these can be used to provide power to the inverter or charge batteries, and in most cases both. But in which case, either one that you use as a primary source must be able to power the inverter and charge the batteries at the same time. Now, we know that the source isn't always available for 24 hours a day. The wind isn't always blowing and the sun isn't always out. So this is where the battery comes in. Now, like a motor vehicle, the battery is used while the primary source is off, or, the engine. Now, how long the battery can provide power will solely depend on its design and capacity, its chemistry. So, a battery will play a big role when the primary power source is unavailable. Now, how long the inverter can function on the battery will depend on the load, or the current draw, duration of the load, the condition of the battery type, and the battery's available ampere hours. Now, I'll get to that in a minute and explain what amp hours is. Now, the most common battery types used with inverters are lead acid, deep cycle, and lithium ions. Now, with lead acid batteries, now you'll find these a lot in vehicles, and these can provide huge current demands in short bursts. Now, like starting a motor, and they should not be discharged more than 30% because it will weaken them, and especially if you wanted to extend their life, which I'll get to in a minute. The deep cycle batteries is found in RVs and marine boats because a lot of the times you're using it when the motor is shut off majority of the time. Now, these batteries are bigger compared to the lead acid counterpart because they are designed to deplete as high as 80% of the battery's capacity. Now, they cannot provide a burst of amperes like the lead acid batteries, but they can provide power longer. The batteries cost a little more than lead acid batteries. Now, you also have the lithium-ion battery. Now, you find these a lot in electric vehicles, but you will also find some of these in deep cycle batteries. Now, these types of batteries can provide a constant voltage and ampere up to the point that they are fully depleted, but are more expensive. Lithium-ion batteries also have a self-discharge rate of 8% per month. Now, because power inverters can draw large current demands, you will need batteries with enough amp hours to provide power to the inverter for the duration till the batteries can be recharged. Well, to do that, you need to understand what the battery's amp hours are. And it's very simple. The amp hours of a battery is measured at 1 amp per hour. Now, this means that if you have a 10 amp hour battery, you can draw 1 amp from that battery continuously for 10 hours. Sounds pretty simple, doesn't it? Well, if the ampere goes above 1 amp, the available amp hours go down. For an example, let's say you're pulling 2 amps from the 10 amp hour battery. All you would have to do is divide 2 into 10 to get 5 amp hours. This means that the battery can provide 2 amps continuously for 5 hours. This is what happens if the rate goes above 1 amp. You just take the number of amps that you're going to pull from it, divide it into the battery's amp hours, and this will give you approximately how long the battery can provide that much current. And as you can see, as the higher the amperage goes, the lower the amp hours drop. Now, to calculate the needed amp hours, multiply the inverter's current draw by the number of hours the inverter will operate on batteries. For example, if the inverter, say, draws 35 amperes for 8 hours, then 35 amps times 8 hours is 280 amp hours. This would be the size of battery or batteries that you would need to provide 35 amperes for 8 hours. Now, this is assuming the current draw is constant, which isn't always the case. But it is the easiest way to calculate because it gives you a more direct approach and a firm idea as to how many amp hours you're going to need. Now, another way you could do this is calculate the average current draw of the inverter. Now, there's no easy way to determine the average unless you actually do the test yourself, or you can make an educated guess using the following formula. Here I have your formula that you can use to calculate the average ampere per hour. And this, of course, is just an educated guess. Now, for the current max, which is represented by the capital I and max, this is the maximum ampere draw from the battery. T active is the time in seconds drawing the maximum amperes. The current minimum, represented by I min, is the minimum ampere draw from the battery. The 3600 is the number of seconds in 1 hour. There are 60 minutes to 1 hour, 60 seconds to 1 minute, so 60 times 60 is 3600. And of course the current average, which is represented by I, AVG, this is what our results will be, the average ampere draw per hour. So let's say the maximum current that your inverter will draw, or your devices, whichever the case may be, is 75 amps. And it's going to do this, say, the first 15 minutes of the hour. Well, all you simply have to do is substitute. Our current max is 75. Our time, which we know that 60 seconds is in 1 minute, times 15 minutes of drawing 75 amps is 900. So now we separate our 900. Now, if you recall, I had 3600 minus T active over on the right hand side of the equation. I'll show you what that's for later, but I have substituted it. Next, we know that the current minimum, let's say, we have 10 amps. So we got 75 for maximum for 15 amps, and we got 10 amps for the remainder of the hour. Next, let's figure out what we need to do. First, we need to multiply 75 times 900. This will give an answer of 67,500. So let's substitute that. Now we have 67,500 divided by 3,600. This is the seconds within the hour. This will give us an answer of 18.75. Now we can substitute that. Now we can do the right side of the equation. But first we need to do everything inside of the parentheses. So that means we need to do 3,600 minus 900. Now remember, the 900 was the 15 minutes that was active, that you're going to be pulling maximum of 75 amps. So we have to subtract 3,600, which is 1 hour, and subtract the 900 seconds, or the 15 minutes, to get 2,700. Now 2,700 is also 45 minutes. This is the other remainder of the hour. Now we can finish the equation. 10 times 2,700 is 27,000. Now we need to do 27,000 minus 3,600, or divided by 3,600. That would give us 7.5. Now as you see the equation, 18.75 plus 7.5 is 1950. This means on average per hour that the inverter would have pulled 19.5 amps on average. This is how you can calculate, or a better educated guess, if you want to average it. Now, what about recharging the battery? Recharging the battery is also important because you need to have enough time to be able to have the batteries recharged to their capacity before you can discharge them again for your long period of time. Even if it's for an hour or 8 hours, 10 hours, you need to have the batteries fully charged. Now, to calculate an estimated recharging time for a battery, you can use this formula. 1.4 times battery's amp hours divided by the charge amp hours. Now, the charge amperes is the amperes that the charging unit is providing to the battery. This will give you the estimated charge time in hours. For example, let's say your battery has 100 amp hours and your charging unit is providing 30 amps to it. If you multiplied 1.4 times 100, then divide that by 30, your approximate recharge time would be 4.67 hours. So this is a fairly simple, but it also depends on the charger and the battery types because they do vary. And it also depends on how depleted the batteries are before you recharge them, which I will get to later. Now, when you're charging batteries, you should never fast charge a battery. There's a lot of risks, especially exploding the battery, which is dangerous. And they don't always fully charge properly. You also have the risk of hydrogen gas building up. Now, you want to use fully automatic chargers. They will automatically monitor the battery. They will charge the battery appropriately. Some of them even have an amperage gauge on them, which that comes in handy so you have an idea how much amperage you're providing your battery. to help calculate your recharge time, but they will automatically condition the battery and charge the battery and maintain the battery while it's being charged. Now, if you're using dual power sources, the primary must be able to charge the battery and power the inverter. If installing in a vehicle, the alternator's amperes must be high enough to power the inverter and the electrical system. This includes charging the battery. Now, let's talk about extending the life of the battery. You never want to use more than 80% of the battery's capacity. This will increase the cycle times, and it will allow the battery to degrade by 20% before you start to see any decrease in runtime. Now, 80% is the maximum that you want to discharge. You can go as 50% if you'd like. The less you draw, the less you deplete, the longer your battery will last, and the less time it will take for it to recharge. Now, since you can't use more than 80%, that means that the battery capacity, say, is 100 amp hours. You can only use 80 amp hours, which is 80% of 100. So, to compensate for the unusable amp hours, divide the needed ampere hours by 80%. For example, let's say you calculated you needed to have 200 amp hours. You would divide 200 amp hours by 80%. Why? It's because 80% of 200 is what? 160? Well, you got to have 200. Well, if you multiply 200 by 80%, you'll get 250. Now, this will allow you to use the 200 amp hours that you needed and use no more than 80% of the capacity of the battery. How? Well, since you can't use more than 80% of the battery's capacity, what's 80% of 250? 200 amp hours. So you're saving your battery by increasing your amp hours by dividing your needed amp hours by 80%. This will give you the boost that you'll need so you can still get your amp hours but only draw 80% of the battery capacity. Next, finally, we have one last thing that we need to consider. And then at the end of the video, I will show you and walk you through the entire procedure from start to finish to help you understand exactly what you need to do or what you need to calculate. So, we need to calculate the battery's amp hours a little bit further. And the reason for this is because batteries react differently to loads applied to them depending on their chemistry and design. No two batteries are the same. Some batteries cut their amp hours capacity in half under heavy loads. For example, if you draw 50 amps from a 50 amp hour battery, well, using the formula before, you should be able to do that for 1 hour. But because of the battery's chemistry and design, you may only get 30 minutes of run time. See the problem? If you had 200 amp hours and you drew 200 amps, you're only going to maybe get 30 minutes worth of it. Now, since power inverters can pull heavy loads on a battery, this can significantly reduce your actual available amp hours under these conditions. So, you'll need to compensate for this problem. To do this, now, remember the calculation we did a minute ago? Where we had to add 80% to 200? Or divide 200 by 80%? We got 250, right? Okay. Well, now we need to take that number, 250, and divide it by 50%. This will compensate the battery's capacity being cut in half under heavy loads. So, we take at 250 amp hours, divide it by 50, and then we get 500 amp hours. That's double. Now, this will compensate for the 20% of unusable amp hours from a while ago, and the capacity being cut in half under heavy loads. So, to run 200 amp hours, you gotta have 500 amp hours. Now, we're going to do the summer here. Now, I will walk you through the entire process, and you can substitute along with me to what you're actually needing. So, what we're going to do is, let's say we have a 400 watt power inverter, and we want to run that inverter for 8 hours. Now, let's use the formulas that we had earlier in this video. Step 1. We need to calculate the 400 watts inverter's input ampere using 12 volts input at 87% efficiency. Now, we already know it's a 400 watt inverter. So, using the formula, watts divided by the result of voltage input times efficiency, which is always represented as a percentage, will equal our input amperes. So let's substitute. 400 watts divided by the result of 12 times 87% equals input amperes. Now, since we got to do everything in parentheses first, we multiply the 12 times 87%. This will give us 10.44. So now the equation should be 400 divided by 10.44. And finally, we get an answer of 38.31 amperes for the input. So this means that the inverter needs 38.31 amperes to provide 400 watts. Step 2. Now, step 2 has two parts, depending on which way you want to go. You can either go ahead and multiply the amperes, which in this case was 38.31, by 8 hours. Because remember, we're going to run this 400 watt inverter for 8 hours. And assuming that we're going to pull 38.31 amps for 8 hours, we multiply 38.31 times 8, using the formula input amperes times the duration on battery, which is 8 hours, will give us the battery ampere hours needed. So, 38.31 times 8 equals 306.48 ampere hours needed. This means this is how much amp hours of the battery will need. Just under 306.5 ampere hours. But if you want to average, you can use the solution in 2B. Now, if you're going to average the input amperes, estimate the maximum ampere draw for the first part of the hour in seconds. And 1 hour is 3,600 seconds. Now, if you need the seconds, take the 60 seconds multiplied by the minutes that you're going to have your maximum input power, or the maximum draw from the battery. Well, let's say that 38.31 amps will be drawn for 1,800 seconds. That's 30 minutes. And let's say it's going to draw 10 amps minimum for the remaining 1,800 seconds of the hour, which is also 30 minutes. Using the formula below, max times time divided by 3600 plus the result for minimum times 3600 minus time divided by 3600. This will give you your average input current. So, next, if you substitute everything, you should read 38.31 times 1800, which is 68,958 divided by 3600. Well, that gives us 19.11155. Now, do the equation on the right. You have 10 times the result of 3600 minus 1800 divided by 3600. Okay, well, let's see here. 3600 minus 1800, that's 1800. Now, 10 times 1800 is 18,000. Now, 18,000 divided by 3600 will give us the result of 5. So now, finally, we need to add 19.155 plus 5 to give us 24.155. This is the average ampere per hour. So you can see it's somewhat the difference. It all depends on your maximum time for the maximum current and the minimum time, or the remainder of the time, for the minimum current. So you see a little difference between 38 and 24. Now this depends on the route that you want to take, how you want to configure up your amp hours. Next, we need to compensate for the 80%. Now remember, in most cases you don't want to go over 80% capacity on the battery. Different batteries react different way. The less you draw from it before you recharge it, the longer the cycles will last. But at any case, you don't want to go over 80%. At any case. So, we need to compensate for the 80%. Now, you need to divide the calculated amp hour from step 2 and multiply it by, or divide by 80%. This will give you your new amp hours. If you used the question or the step in 2A, 38.31 divided by 80% equals 47.89 amp hours. If you used step 2B, then 24.155 divided by 80% is 30.20 amp hours. This is to compensate your 80%. Now you can still get your 38.31 or your 21.155 amp hours depleting the battery no more than 80% by using your new amp hours on the battery, 47.89 and 30.2. This will allow you to deplete your battery for 80%. Now, we also have to compensate the capacities of the battery being cut in half under heavy loads. So finally, we need to do your new amp hours from 2A or 2B and multiply that or divide that by 50%. So the formula would be amp hours, or your new amp hours, divided by 50%. This will be your final amp hours you will need. Finally. So if you did 2A, which your new amp hours would have been 47.89 divided by 50%, this would give you 95.78 amp hours needed. 2B would have gave you 30.2 divided by 50%. The answer would be 60.4 ampere hours are needed. And this is final. This is your final result of the amp hours you would need to provide your 400 watt power inverter for 8 hours. Now, as I said, you can substitute. I'm just showing a demonstration of how to calculate the formulas, how to use the formulas, and how you reach your final result as to what size batteries and amp hours you will need. So, here you have anywhere between 60.4 amp hours and 95.78 amp hours to operate your 400 watt power inverter for 8 hours. Now again, you can substitute with your own calculations. I'm just showing you a demonstration how to calculate it. Now, finally, all you have to do is calculate how long it would take to charge your batteries. Again, you take 1.4 times the battery's amp hours divided by the charging amperes, which is the amperes that your charging unit is providing. This will give your estimated recharge time in hours. So let's take the first one, which was done from 2A. Let's take 1.4 times 95.78, divide that by 10, since 10 would be the charging amperes. We get a result of 13.4 hours to recharge. Now let's take the average one that we use using step 2B and take 1.4 times 60.4 and divide that by 10 amps. This gives us 8.5 hours to recharge. This is all you have to have or need to configure what your batteries, what size you'll need to operate all your devices from the batteries for a period of duration. Whether it's an inverter, lights, radios, TVs, anything that run on 12 volts, this is how you figure out how many amp hours you will need to run for a period of time. Now, you'll see batteries that have cold cranking amps. And this picture here, you'll show a demonstration here. It's a 12 volt battery. It shows cranking amps, which is 845. And the amp hours, which shows at 1 amp, and this is how they're rated, shows 125. Now you can hook these batteries in parallel to add up your amp hours. And the same rule applies. You don't want to fast charge these either. But you want to get a good quality charging or regulator to charge these batteries to make sure that they're not overcharged. You don't fast charge them. You want a fully automatic charger that will automatically condition, charge, and maintain the battery until it's used again. Well, this is a video about inverters and batteries. I hope it's helped you on your projects. If you need anything else, you know how to contact us. Thank you for watching.